We're going to take a closer look at the ideal gas law and a couple examples of the kinds of problems we can solve with it. Okay. The good part about this passage of the course when we're talking about ideal gases is that your base equation for just about everything you're going to do is going to be that PV equals nRT equation, which you pretty much already know, right? So you're unlikely to find yourself stumped saying, I just can't remember what the equation is or how I do this, right? That equation, as I think I mentioned in the previous video, was originally based on just observations, people doing experiments on assorted gases, a lot of them air, and making observations about how the various properties they could measure were related. Okay. I also mentioned you could derive this by doing some physics with some assumptions about molecules. A little bit of a hint of how that would go if I take this little insert here in the figure and imagine this thing over here. This is the wall of the balloon there, right? And the molecules are crashing in there, right? So say this molecule here comes in and hits the wall, it comes in and it's going to hit the wall of the balloon, it's going to bounce off and it's going to go back in the opposite direction. When it does that, it's going to change its momentum because it goes from moving this way to moving that way. And that means the momentum is imparted to the wall, right? And so if we do a physics problem and figure out that change in momentum, for example, we can use that to begin to process towards deriving the gas equation itself. That's also where pressure comes from. The pressure of the gas comes from the force that the molecules are exerting when they bounce off those walls. I'm going to talk about most of the pieces here in one by one. Pressure is a quantity we haven't worked with before because it really applies pretty much only to gases. We don't talk about the pressure ordinarily when we're not talking about gases. Dimensions for pressure are force over area, right? So you'll hear people say pressure is force per unit area. In SI units, that means the unit of pressure should be newtons per square meter, right? That unit gets its own name. It is called Pascal. That's a pretty uncommon unit, honestly. It's just not popular in most areas of interaction with gases. Things we will see more commonly in our course and in this country include the atmosphere, where 1 atmosphere is essentially the nominal pressure of the atmosphere at sea level on a normal weather day, right? Official conversion factor between atmospheres and pascals is this number here. 1 atmosphere is 101,325 Pascal, okay? Atmosphere is a common unit of pressure for pressures that are, well, atmospheric pressure or above. For pressures below atmospheric pressure, if something is under some level of vacuum, we very often will see pressures expressed in torr. Torr is a shortened form of the name Torricelli, who is involved in sort of the history of pressure measurement. 760 torr is equal to 1 atmosphere. Okay, the torr has a little bit of a curiosity about it. It is also sometimes referred to as a millimeter of mercury. And that should bug you because a millimeter is very clearly not something that translates to force over area. Okay, that millimeter of mercury unit, that owes its origins to the good old-fashioned mercury barometer. There's a little picture here that shows how that would work. There's a pool of mercury down in the bottom here, the liquid metal. The way this gets started is that tube in the center would get filled with mercury and then flipped upside down into the mercury pool. When it does that, there's a bit of a vacuum space up here, right? And the height that the mercury rises up in that tube is going to be a function of pressure because the higher the pressure gets, the more force is pushed down here on the surface of the pool of liquid mercury, and that makes the mercury rise up in the tube. Okay, this height up here, if we're at 1 atmosphere pressure, that would be my 760 millimeters of mercury, because that's how tall that thing would be. Okay, and so 1 torr is the amount of pressure that it would take to change the height of that mercury column by 1 millimeter. In engineering fields, you may often see pounds per square inch. 14.7 pounds per square inch is equal to 1 atmosphere. Okay, the torr in the atmosphere, those are our big ones that we'll see in problems that you'll see in this course. Okay. Not going to talk about volume because we've talked about volume before, right? Volume is just in length cubed. For gas problems, volume is most commonly expressed in liters. If the volume is not originally in liters, we might have to change it into liters to make things work properly. We'll see. The gas constant, R, this is also officially known as the universal gas constant. Universal because there's not like a separate version of the ideal gas law for oxygen versus for helium versus for nitrogen or anything like that, right? There's just one version of the gas constant for all of those things. It is an experimentally determined property, right? So if I take the gas law PV equals nRT, and if I just solve that for R, I'd get R equal to PV over NT. So if I take a sample of gas, and if I can measure PV, N, and T, all of those things at the same time, then I'd be able to get a value for R. And that's where this value comes from, okay? In SI units, R is equal to 8.314 joules per Kelvin per mole, okay? Joules per mole Kelvin, I guess I wrote it that way. That value is very seldom used in gas problems, and the reason for that is for that one to work out comfortably, we would need our pressures in pascals and our volumes in meters cubed, and that's not usually how things happen. So that value you're not too likely to want to use in a gas law problem anytime soon. The two that are most commonly used in problems set up the way we will in here are on the bottom, 0.082, that's in liters atmospheres per mole per Kelvin, or 62.36 for liter torr per mole per Kelvin. Right. Now, a lot of times students say, like, well, how do we know which is the right R to use? Okay. And the answer is they're all the same quantity, right? There's no right R or wrong R. They're just in different units. To prove that to yourself, if you want, we said on the previous slide that there were 760 torr in 1 atmosphere. So if I take this 0.082 number and I multiply it by 760, what should I get? According to what's on there, I should get my 62.36, right? Because that's just saying I'm converting these atmospheres into torr, and to do that, I would multiply by 760. All the other units stayed the same. Right? So it's just a unit conversion, the change between these different quantities. So when you work with the gas law, if you get a gas law problem wrong, by far the most common way to do that is to do something foolish with units, okay? I have certainly seen students do lots of crazy things with units, most often because a lot of students don't write units down, or you go directly to typing into your calculator and then you don't realize you've got things stacked up in a way that makes your units not actually parse out to what you want. Okay. So the most important thing is to make sure your units are consistent. There's not right units and wrong units. There's just like, do they all match up? So if you're solving for volume, for example, you need to arrive at units that are volume units and not have a pressure unit hanging around or something like that. Two ways you can do this. One way, which is sort of suggested here in the slide, is just take your P and V in whatever units they come in or whatever units you like. If you do that, then you could choose an R value that matches those units and life will be simple, right? An alternative way to do things, and one that I actually often do, is for me that 0.082 value of R. That's the one that I know like the best and know that I'm not going to get wrong. So often if I start with a problem in torr, I might turn the pressures from torr into atmospheres just so I could use my 0.08206 number and not have to remember or sort through what are the order of the digits in the value of R with torr, right? If you're looking it up, you can just look it up in whatever units match what you're working with, and that would be fine. When you take your next quiz or exam, well, not the one right after this, but the one that will involve gases, you'll probably be given R values in multiple units, in more units than you really want them in, probably, to be honest. So the one quantity that you have to be really careful about for units in the gas law is the temperature, okay? And I'm going to try and explain here why that is, what makes temperature special. So just to see why it's special, if you look at the gas law here solved for volume, it's nRT over P, right? So if I take the limit where temperature goes to 0, just imagine I cool the sample off, it's getting colder and colder, I want to go all the way to 0 temperature, that equation says the volume has to also go to 0, okay? Saying the volume of my gas goes to 0 says my gas disappeared. That's a problem, right? That's not what would really physically happen. So having that happen at an ordinary temperature would be quite bad, right? If that happened at 0 degrees Fahrenheit, for example, it's not, well, here in College Station, it's uncommon, but not totally unheard of for the temperature outside to get as cold as that. There are other places where it is quite common. There are places where we might get semi-regularly to 0 degrees C. I used to live in Chicago before I moved to College Station a long time ago, and that's definitely a place where that can happen. And so it's obvious that the volume of gases doesn't go to 0 when we get to that temperature, okay? Volume of gases doesn't really go to zero when we get to 0 Kelvin either, but that's another story. So why is it that temperature doesn't work like other units, right? I can put the volume in any units I want. I can put the pressure in any units I want, but the temperature I can't. The reason for that is temperature scales are defined in a wildly weird way compared to other things, right? If you're measuring volume or you're measuring pressure or you're measuring mass or distance, no matter what units you put your quantity in, 0 still means the same thing, right? If you say that the mass of something is 0, that means there's no stuff there, right? Then it's 0 milligrams, it's 0 grams, it's 0 kilograms, it's 0 pounds, it's 0 tons, it's just 0, there's no stuff, right? You don't have to add or subtract to change those units. When you change temperature units, you have to add or subtract in addition to multiplying, dividing, right? And so because the 0 point moves around on the different scales, that's why we can't just hop between temperature units in the same way. So for our purposes in here, we'll always be using Kelvin in the gas law. Basically, anytime you're multiplying or dividing by a temperature, make sure you're in Kelvin on an absolute temperature scale. Absolute scale means it has the 0 point at what is the so-called absolute 0 temperature. Okay, 0 Kelvin is equal to, as it says down there, minus 460 just about degrees Fahrenheit, which is obviously very, very cold. In Celsius, 0 Kelvin is minus 273.15 because there's the opposite. We can get that from this conversion that's here, right? So if you start off with a Celsius temperature, you're just going to add 273 to get to a Kelvin temperature. Some of you, depending on your field, may at some point encounter the Rankine temperature scale. Rankine is a temperature scale that has degrees the same size as Fahrenheit, but is an absolute scale, so it's 0 is at absolute 0. Okay, so between Fahrenheit and Rankine, you can convert just by adding and subtracting. That would also work in the gas law, but we are not going to use that in our course. But I mentioned that just because some of you may see that or may have seen that unit somewhere else. I'm going to do a couple of problems here involving the gas law. The first is the simplest possible case, right? The simplest possible case says of PV equals nRT, right? R in there is a quantity we always know. That's a constant. It's just a universal number. We look it up. Okay, so that says there's 4 variables in this equation, P, V, N, and T. If you know 3 of those and you're just looking for the 4th one, that's the easiest possible gas law problem. Okay, you should just rejoice when you see that problem. And then after you do that, you should be careful of your units because that's how you're going to get it wrong if you're going to get it wrong, right? As a somewhat weird example, just to illustrate this, and to also make a point about numbers of molecules in a gas, I'm going to estimate the number of molecules in a spherical container with a 4-inch radius somewhere near room temperature and pressure, okay? So let's just go ahead and do this, all right? So I am going to take my room temperature and pressure, like I just said. I didn't actually put that in the thing, but I'm going to take, let's say, P equals 1 atmosphere. I'm going to take T as 298 Kelvin. Okay, and I'm going to get V from this radius, okay? V, volume of a sphere, is equal to 4/3 pi r cubed. If I put in this case, that's going to be 4/3 pi times 10 centimeters, because 4 inches is 10 centimeters cubed, right? 4 inches here, if you just multiply that by 2.54, I'm going to call that 10 centimeters. Okay, so that says my volume comes out to be, it's 4.19, it says in my notes over there, times 10 to the 3rd. That's in centimeters cubed. 1,000 centimeters cubed happens to be a liter. So I'm going to say I know that that is 4.19 liters, and that's the unit I'm going to take over here with me when I do my problem. So now I have V equals 4.19 liters. That's going to give me N. N is equal to PV over RT. If you do dive into a problem and start by writing down something other than the actual PV equals nRT equation, I do encourage you to double check and just look at it and make sure you didn't flip something upside down, because you'll feel dumb afterwards if you get something wrong that way. Then my pressure, I said, is 1 atmosphere. My volume is that 4.19 liters I just came up with. R, I'm in liters and atmospheres, so I'm going to do 0.082. And my calculation probably has some other digits after that, because I'm like that. Liters and atmospheres, notice I almost wrote the units down wrong, over moles and Kelvin. My temperature is 298 Kelvin. I swear I'm writing a K there. Okay. And if I multiply all that out, my notes say I get about 0.17 mole. That was a 7 when I wrote it, really. All right. If I want to get to molecules, which was the actual question, all I have to do is take my 0.17 mole and multiply it by Avogadro's number. When I do that, my notes claim I get about 1 times 10 to the 23rd. Sorry, my pen on the iPad is acting very strange right now, so I'm going to try and get through this one. And that's now in molecules. So I'm going to write something like that and stop because it doesn't want to write there right now. Okay. One of the points I want to make from this is a relatively small thing, right? It's it's a 4-liter thing, so it's a volume that's gosh, a bit bigger than a giant bottle of soda, right? And it's got 10 to the 23rd molecules in there. Okay, so any sample of gas is always going to have a lot of molecules. We said to be an ideal gas, it was supposed to have a really large number of molecules. There's no way that's not going to be true, right? We'd have to be to a very, very, very small pressure and almost unachievably small pressure in order to have that postulate or that assumption be not correct. All right. The other kind of problem I want to talk about is what in chemistry teaching we at least refer to as a change in conditions for the gas. This is where you know some stuff about the gas initially, and then it says you're going to change the temperature to something, or you're going to change the pressure, or maybe you're going to change 2 things. Okay, there's 2 possible ways to do this problem, these kinds of problems. One way, the way I very much do not recommend, is to try and remember a whole bunch of special case equations. Okay, you may in a high school class sadly have been taught that you should remember Boyle's law and Charles's law and Avogadro's law and things like that. Okay, which are all little subsets of the variables in the gas law. And if you successfully remember all of those equations and use the right one, it's true, you will get the problem correct. But suppose you don't want to remember all those different equations. Suppose you want to say they're all baked into the ideal gas law, right? And the ideal gas equation is one that you're very unlikely to forget or to get twisted around. Okay, so what I like to do is I like to start from the entire ideal gas law, and then I'm just going to get on one side of the equation all the things that are changing, on the other side of the equation all the things that are not changing. Okay, and then I can solve the problem from there. Best way to illustrate this is with an example. So let's take a look. All right, this is an example of the second sort of problem that we could do, the one where we're going to do this part of putting the things that are changing on one side, the things that are not changing on the other, and then working from there. Okay, so I have a bulb. It's got 760 torr. That's 1 atmosphere of methane in it at 25 degrees C. It says that I know, I'm going to assume my bulb is rigid, like it's made out of, I don't know, glass or something like that, okay? So it's not going to expand like a balloon when I heat it up. The bulb may burst if the pressure exceeds 2 atmospheres, okay? So if this was something that was going to get hot, I'd want to know, is it safe for it to get that hot, for example? If the bulb is heated, at what temperature would the pressure reach 2 atmospheres, okay? So let's think about what's changing and what's not here. Notice that we don't know anything at all about the volume of the bulb. That's kind of why I said I have to declare the bulb to be rigid, so that I'm going to say its volume does not change significantly, okay? Let's write down our whole gas law, PV equals nRT. All right, I know that pressure is changing. Right, pressure definitely changes because I can see I'm going from 760 torr up to 2 atmospheres, okay? I know that T changes because it says I'm heating up the bulb, okay? What doesn't change? We're gonna say constant. Things that don't change, we're gonna say volume doesn't change, right? We're going to say the number of moles doesn't change because it doesn't say we opened the bulb or anything like that, right? The gas is trapped in there. Same molecules are still in there. So N is constant and R is always constant. Okay, so what am I going to do? I'm going to collect up the things that are changing and the things that are not and put them on opposite sides of the equation. Okay, that says I'm going to say that P over T, because those are the 2 things that are changing, solve the gas law for P over T, and on this side I will get NR over V. Because NR and V are all constant, that says this ratio is constant. right? Make sure that makes sense to you. But if neither N nor R nor V changes, if those all stay the same, then that ratio has to stay the same too. There's no way it can change. If this stays the same, then this one has to stay the same too. So that says the equation I want to use for this is one that I might write and would usually write as something like P1 over T1 equals P2 over T2, where the ones and twos kind of refer to before and after the change that's going to take place when I heat up the bulb. Okay, that's my equation for solving the problem. Actually, deriving that little equation starting from PV equals nRT, once you're comfortable and have done this a couple times, it takes no time really at all. I know I made a process of it there because I'm trying to make the point, but you can do that really quickly. And for me, it's not worth trying to remember a whole pile of equations when you can do everything you need to do starting with just PV equals nRT. So let's solve the problem from there. These are the parameters I've got, right? At the original conditions, I'm going to call that 1. I had 760 torr for the pressure and 25 degrees C, which I'm now going to call 298 Kelvin for the temperature. Okay, I want to know what the temperature will be when I get to 2 atmospheres. So I'm going to say my equation said P1 over T1 equal P2 over T2. We want to know T2, so let's solve for T2. T2 is equal to P2, still having issues with the writing, over P1 times T1. I do have to make sure my units are the same here. So I'm going to transfer my 760 torr. I made it easy for myself. That's equal to 1 atmosphere. So I'm going to go into atmospheres. I get 2 atmospheres up here. I get 1 atmosphere down there. I get my 298 Kelvin here. Right? And if I solve that, I get 596 Kelvin. Which is equal to 323 degrees C. So that would be like a reasonably hot kitchen oven, okay? So it's not an unachievable temperature. If for some reason I was gonna put this bulb in an oven, I'd have cause to make sure that I was convinced that was a good idea, all right? Notice I wrote down my pressure units here. It's a good idea to do that because that makes me make clear that they're both in atmospheres, and so the pressure units disappear. I'm left with only temperature. Right? If I had put my 760 down here, obviously I would have gotten a different number when I divided. I would have said that the temperature was getting colder while the gas was, the pressure was increasing. That wouldn't make any sense. If I wrote down the units, I'd realize that I didn't get to Kelvin. I got to atmospheres Kelvin over torr, and then I would know I had a problem that made that, that mess of units turn out. Okay. Again, that's definitely my preferred approach for solving problems that involve this change of conditions. In this case, we have 2 things changing. In other cases, it could be 3 or whatever, but it always works if we do this. And it lets you always start off saying the starting point is PV equals nRT. That's the one equation you're the least likely to forget, probably of any that we use in the course, to be perfectly honest.